Hello, calculus fans. All right, we're going to talk about arc length here. We're going to measure the lengths of curves. Now we can easily measure the length of line segments. That's no problem. We can even measure the lengths of things that aren't straight lines, curves like circles or arcs of circles. But interestingly enough, even for very simple curves, we have no way of measuring their lengths. Okay, so here's a really simple one. What is the length of the curve y equals x squared between 0, 0 and 2, 4? How long is that curve? And what's interesting is that right now we actually have no way of measuring the length of that curve. All right, so let's take a curve y equals f of x between x equals a and x equals b, and let's assume that it's smooth. And what we mean by that in this case is that let's assume that f prime of x is a continuous function. So there are no sharp points on the curve. Now we're going to create a polygonal path. What we'll do is we're going to choose partition points x0, x1 up through xn in the usual sort of way. And then we're going to create the polygonal path by playing dot to dot on a bunch of points on the curve. So we take the point x naught, f of x naught, that's the first point on the curve, and then we move over to x1, f of x1, and instead of following the curve, we follow a line segment between those 2 points. And we keep creating line segments to join together until we're all the way at the very end. The last point will be x sub n, f of x sub n. We'll look at a picture of this in a moment. The usual sort of thing, we're going to let delta x be equal to b minus a over n. Now this polygonal path that we're going to create will approximate the curve. And it does so in such a way that as n approaches infinity, the length of this polygonal path should approach the length of the curve. All right, so here's what we mean by a polygonal path that approximates the curve. So we have y equals f of x, that's sort of underneath in the pencil, and with the blue pen we see that we're joining points. You can see the first line segment along here joining x naught, f of x naught, and x1, f of x1. And then we keep doing this, we keep joining points together, we keep moving over to the right by an amount that's delta x, and we keep joining up these line segments. Now it's fairly straightforward to compute the lengths of these line segments, add it all up, and then in the end we take a limit, and that should give us the length of the curve. So on one of these line segments, on a single line segment, that is the path from xk minus 1 f of x sub k minus 1 to xk f of xk, the polygonal path has this length. We'll just call it d. And it's equal to the square root of the differences between the x's squared plus the differences between the y squared. This is just the Pythagorean theorem in action. So it's the square root of xk minus x sub k minus 1 quantity squared plus f of xk minus f of x sub k minus 1. That one's squared also. And then we take the square root of the whole thing. If we factor out f of xk minus f of xk minus 1, we get a new expression that looks like this. And then we're going to rewrite it in a funny way. So first of all, the f of xk minus f of x sub k minus 1 turns into delta x. And then this quotient here turns into f prime of xk star. And that's true for some x sub k star in the interval xk minus 1 to xk. And the reason we can do that point exists by the mean value theorem. This is a theorem that came up in Calculus 1. We haven't used it for very much. It's sort of a theoretical thing that allows us to make this choice. Remember that the mean value theorem just says that if you have a curve that goes between points A and B, and then you draw a line segment between those 2 points, that there's some point in between where the tangent line to the curve has the same slope as the line segment. So if that's one polygonal path segment, then if we add up everything, then we'll get the sum of all these things. And then the whole point of doing this is that what we see here looks like a Riemann sum. And so we'll define the length of this curve to be the limit of this Riemann sum, if that limit exists. So L is the limit as n goes to infinity of the sum, where k goes from 1 to n, of the square root of 1 plus f prime of xk star squared delta x. That, of course, turns into the integral from a to b of the square root of 1 plus f prime of x quantity squared dx. Which means we can make a definition of arc length to say that if we have a smooth curve defined between a and b, then the arc length of that curve is going to be defined to be that integral from a to b of 1 plus f prime of x quantity squared, square root of that whole thing, dx, if that integral exists. Okay, that's all for now.